So my name is Yves Hagedorn. I'm heading the company Aconity 3D. And today I would like to talk a little bit about progress and current challenges in online process control for L-PBF. So for those who don't know us, what do we do as Aconity 3D? Well, we do everything which involves laser-based 3D printing, what we call LBM, of metals. So of course all that starts out with consulting. There's also some job shop involved, material distribution, most importantly however testing facilities, so we can enable our customers to process their individual materials for their specific application. And in the long run, everything evolves around us, providing equipment, providing machinery for the industrial application in question. So these are our systems, at least 4 of our systems. We have some more, so you can visit our webpage to see a little bit about that. So starting on the left-hand side with our largest system, which is the Aconity One. So this is a system meant for production of laser-based processes. So it's a multi-laser system, and you can actually build pretty large parts, 400 millimeter in diameter, 400 millimeter high. This is followed by our second largest system, the Aconity MIDI Plus. So this is also available in multi-laser configuration, but most importantly, we have developed that system to enable multi-material L-PBF process. And I believe we are the first ones on that, so we will see some more on that later on. So the Aconity MIDI Plus comes from the Aconity MIDI family, which is designed towards having a flexible platform and a retractable or extendable process chamber. So you can actually, what you see on the Aconity MIDI, have an extra process chamber which facilitates setup times for your process, and so you can parallelize manufacturing and get a better economics on your cost per part, so to say. And our smallest system, the Aconity Mini, which is our entry-level system, perfectly suited for fast material checks and design of experience, but also production of, let's say, dental. So what's different with us from other machine manufacturers is maybe the fact or the possibility that you as a customer can configure your system towards your specific application. So actually everybody of you can visit our webpage, www.aconity3d.com, and you can configure your own system just like you're used to with your car. That originates from the idea that for dental applications, you need different hardware than if you would want to process parts for automotive applications, so to say. So here in the example, we see an Aconity MIDI, and you can actually choose between which lasers you want to use on the upper left-hand side, so 200 to 1000 watt lasers, so how many you want to use, which scan head technology you want to apply, do you want any process monitoring, in this case pyrometer and high-speed camera. Also on the bottom, I think we're the only one providing high temperature preheating, enabling processing of difficult to weld parts. So we go up to 1200 centigrades, which is more meant for die-hard material research, but the lower temperatures can also be applied for aging steels and titanium aluminides, for instance. On the left-hand side, also meant more for, I call die-hard research, so to say, is the vacuum module. So for industrial applications, that enables you to actually decrease purging time and then run your standard process. But you could also run your process under less than 1 millibar absolute atmosphere. And that has some pretty nice capabilities for research. Further, what we see here, which is exclusive for the Aconity MIDI, exchangeable process chamber. So if you have only 2 materials in question, you save a lot of cleaning effort. And trust me, I've cleaned a lot of systems. So all that is held together by our Aconity Studio software. So that also provides a Python API, which is actually, I believe, the reason why I'm presenting here today, because if you work with Dyndrite, you've noticed that they also apply Python. And so that's a perfect link. So the data preparation software can now communicate with our Python API and enables a whole new lead in terms of data preparation. So let me maybe talk a little bit about some success stories. So what you see here is our high temperature preheating at 1200 centigrades actually. So it glows nice and easily. So what we wanted to do here is process titanium aluminide, which is exceeding the state of the art. So actually, if you apply a rather low temperature preheating of 800 centigrade, you actually succeed in processing that thermite, that really difficult to weld material. And judging by the mechanical properties, this process then also outperforms what is at least found in literature for competing processes like EBM or casting. So you can improve the properties for LBM parts with flexible systems. Also, what we've done here is just integrating a green laser. A lot of companies talk about green lasers, and since our systems are that flexible, it's basically just exchanging a laser, well, maybe also the coating of the scan head. But in the long run, that allows you to process pure copper. And that is new. TWAMF has a system which can do that, but that's really important because if you process pure copper, you enable a whole lot of new applications here. Another application we are really proud of is what we've developed with Aerosint is our multi-material LBM process. So we have teamed up with Aerosint, and they've actually provided a recoater which is capable of processing or of depositing different materials. In this case, copper, chromium, and steel. And the data is synced between the recoater and our laser, so we can actually apply different parameter sets for different materials. And what you see here is the first true multi-material part in X and Y and Z direction built with LBM. So what we also do, of course, we are an offspring of the Fraunhofer Institute for Laser Technology. So we believe that laser is our bread and butter. So what you see here is our multi-laser process. So that is, of course, really, really neat. We've heard about that yesterday also already from SLM Solutions for pushing the boundaries in terms of cost per part, meaning you can actually be a lot more productive if you have multiple lasers working on one part. However, since we have full overlap with our multi-laser system here in a 400mm build bed, we can actually provide something which is quite neat, called the AES. That's what we call it, the Advanced Exposure Strategy. So that allows you, and that's a screenshot from our software, to have one master scanner and a bunch of slave scanners. And instead of choosing the scan speed of your slave scanner, you get to choose the delay to your master. And then you get to choose something different, like do I want to modulate my laser power? Do I want to wobble? And that opens up quite some interesting possibilities. So what you see here, you could have your main laser and your second laser wobbling around it, or the wobble with an additional offset, or have the main laser focus and the secondary laser defocus, or go completely nuts on it. So that opens up a lot of possibilities in terms of heat treatment in process and manipulating your microstructures, which is potentially really, really, good. So what we see here, more to the topic, is our process monitoring. So here's actually a video, in-process video of our high-speed camera. So what you should see on the left-hand image, I don't know if you see my mouse, maybe I try to show a laser pointer, is the spot which is turned off and on. So that's a modulation. So what you see, the contour of that scan part is not necessarily well defined. So what you can do now, once you get the possibility to take a look at your process, change these parameters and take a look at the process, adjust the next layer. And you see, by just changing the modulation frequency and length, we get a lot better defined contour. So that is a really, really strong tool, this process monitoring, to actually get an in-depth understanding of the process itself and do fast and efficient material research and enable new materials for additive manufacturing. Another process monitoring tool is the pyrometer. So what you see here also is it's coaxial, similar than the high-speed camera, means that we always measure the heat radiation emerging from the interaction of the laser and material. And what you see here, that would be the first scan, because we know where the scan head is positioned. So we can calculate that, what we call emission map. So the first scan is done here. It's a little bit colder, a little bit bluer, and you see the shorter the scan vectors, the hotter it gets. And that's state of the art, that's standard. So that's bad news, because the heat history of your part will change, and that has an influence on your microstructure, but also on your geometric accuracy, since your melt pool will be larger, right? So what we now want to do is actually not only do process monitoring and provide that data to customers, which we already do, but also do process control. So we distinguish between 3 different process control steps. The first one is between 2 jobs. That's pretty standard. Take measurements, take a look at your parts, see, okay, that's good, that's not so good, change my process parameters. A little bit nicer is between layers. So that involves high volume data and in-job reaction, which can potentially be done with Dyndrite Python API. So we can change that. And sorry, I need to jump back. And the fastest one is in process, in layer, means you react really, really quickly on changed heat conditions of your part. So between each layer, or layer by layer, we see again an example here. So again, shorter scan vectors, it's hotter. So from that knowledge, you can basically react to that by zoning within Dyndrite, so to say, to choose different parameter sets for that area. And that enables you to have lower laser power for shorter scan vectors, so less overheating, and that's potentially good news. However, the holy grail, of course, is to be able to react in process, have in-layer control, and that's what we are chasing after, honestly. And that's a picture we have actually taken from our process with our sensors. So that's a bridge. Everybody knows overhangs for this laser process are difficult to process. And you see there's, from the pyrometry data, you see there are some defects here, non-controlled. So what we have implemented now is a P controller. You see a lot more homogeneous is the sensor data. And if you apply a PI controller, it's even better. So what does that mean for the real world? Well, it means we are actually, capable of counteracting issues within your part. So that is an example for a steel part in which we have applied our control. So you see there are defects in the bridge, which is standard to the process, so to say, and you see the sensor reading. So if we apply our PID controller values, we can actually enable printing steel as it should. So the machine controls itself in layer, and that's new, I believe. However, that changes tremendously for different materials. Even the same material with a different powder size fraction, so to say, radiates heat differently. So that is just work in progress for us. We showed that it's possible, but we cannot finish until we allow our customers to actually change those parameters for themselves, for their part or material in question for the application. So even though it was just a really, really short talk, 50 minutes, but I'd like to conclude real quick. Additive manufacture of metals, we believe the full potential is not yet reached. We want to be a partner for innovation. So hit us with your applications. We will be there later on at the vendors launch. We believe the material choice is extending through flexible equipment. We've shown that. And process monitoring, for once, allows for extended capabilities in error detection, which is important for standardization. But process controlling, the next step, the holy grail, that is what we've shown here, first application, and there will be definitely more work to come.
All right. Great presentation, Yves. We just have time for one question. We've got a question from Anonymous. Congratulations on achieving multi-metal capability. How do you make sure the interface between each metal has a sound metallic bond? What other materials can you print as a multi-metal part?
Great question. Thank you for that. We believe there's a large research market here, so to say. So our approach is always open innovation. So we want to deliver tools for our customers so they get the chance of taking a look at it. We strongly believe we cannot take a look at all materials out there because every application calls for a different material and there are difficulties in different materials bonding with each other. Just take iron and aluminum, for instance, or titanium and aluminum, what I've shown. So we just provide the tools and customers can do it on their own, or we engage in a project jointly and we show the feasibility and then provide the system for the application of the customer.